In this video, we will talk about AlexNet, which is next big step in deep learning, or you can specifically say computer vision. I am Ritik Dutta and welcome back to my YouTube channel. So today in this video, we will talk about the basic of AlexNet, like its introduction, when it was founded, how it is similar to us in distinguishing different objects, what are features, padding, polling, and more. How AlexNet was built, and the mathematics involved in the process of making AlexNet, like how number of layers are calculated. Then we see different techniques used in the AlexNet, in which some of them were used for the first time. And lastly, we are going to train a road model based on AlexNet architecture. AlexNet was designed by Alex Krzyzewski in collaboration with Ilya Sutskever and Jeffrey Hinton, and won the 2012 ImageNet competition with a top 5 error rate of 15.3% compared to the second place of 26.2%, which is a huge margin. So, AlexNet contains one input layer, 5 convolution layers, 3 pooling layers, 2 fully connected layers, and 1 output layer. But wait a minute. First, let's see how computer vision sees the world. Now, this is our scene. I know, not looking great, but yeah. So, here we know it's a hut. But how computer vision knows it as hut? So, in computer vision, it takes different features and relate them with each other and predict the closest outcome. So, on a larger scale, what it does is collect as many as finest detail in the picture, like vertical lines, horizontal lines, circles, etc. So, in this picture, it takes these vertical lines, these horizontal lines, and diagonal lines as separate features and combines them to form a sub-feature. So we can say that these lines are our smallest feature, or you can say initial layer features. Like these features combine to form windows, these features combine and form hut, these features form doors, and these features form hut's top. Now these are also called features, a step ahead from the initial ones, or you can say level 2 features. These features give us more clearer picture what the image is about. After that, these all features combine and give us the final output, which is our hut. Now we know how computer vision sees the world. Now let's see how it extracts the features from the images. Here is our number 6. It contains many features like circle, diagonal lines, vertical lines, and more. So how does computer extract these features? It does that with the help of filters. Filters are set of learnable weights. You can think of each filter as storing a single template or pattern. These are the set of numbers arranged in the different pattern, which is superimposed on the image to extract a particular feature. So suppose we have this number 6 image. Now, as we all know, the image is nothing but a set of light and dark pixels. So we convert this number 6 into pixels, so we can understand it better. As we know, the number line for colors are 0 to 256, in which 0 is for black and 256 is for white, which is, for simplicity, we take only -1 and 1 for black and white pixel. So the boxes where number 6 lies will be updated with -1 and the rest with 1. So our pixel map for the number 6 will look like this. Now suppose we want to extract circle feature from our number 6. Then we multiply our image with this filter. This filter will extract all the circle patterns from the image. So first our filter will be superimposed on the input image, as you can see here. Now the first number from our input image, or you can say blue box, will be multiplied with the first number of filter. Then we add this to the second number from our input image, multiplied by second number from the filter, plus third number from input image multiplied by third number from the filter. Notice that we have not taken the fourth number as -1, which is actually the fourth number of the entire input image. But if we had taken the fourth number from the smaller grid, which were superimposed by the filter, which you can see as the blue box. Similarly, the process will continue until the ninth box. Then we will divide our equation with the size of the filter. In our case, that is 9, which is equals to 5 upon 9, which is equals to 0.55. Then we put this number into a new matrix, or you can say filter map or output image. Now we shift our blue box one position to the right. Now that shifting the blue box by a certain position is called stride. In our case, the stride is 1 by 1 because we are shifting our box one place at a time. We can also shift our box 2 at a time. In that case, the stride will be 2, or stride can also be more than 2. Now, the previous process will continue and we put our answer as the next index of the matrix. Similarly, the process will continue until we multiply all the input images to the filter. You may be thinking, how we already know the size of the output matrix? So, this is the formula for that, which is input size minus kernel size upon stride plus 1. Now, you may be thinking that our input image is now shrinked to 4 into 4 matrix. So, to fix this, we can also make our output matrix same as our input image by adding padding to the image. Padding is the process which let us maintain the size of our image and gives corner pixel the same priority as the middle pixels. You can get how much you need to add padding to make your output matrix same size as your input matrix by this formula. But in programming, you don't need to remember this formula. Everything is simple there. Now you are noticing that all the numbers from the output matrix are less than 1 and only one number at the bottom left is equal to 1. This means that a circle pattern is present at the lower left side of the image. Now there is another term, pooling. We use pooling to shrink the size of our output image so it doesn't consume much memory while maintaining the important details, also reducing the chances to overfitting. We do this by dividing our output matrix with equal window size and take the maximum number from that window. In our case, this window will be of size 2 into 2 and maximum number from that window is 0.55. Next, this will be minus 0.33. Next will be 1 and next will be minus 0.11. This is called max pooling. You can also take average of this number instead of maximum. Now that we know about feature extraction, padding, pooling, let us move to the next section. Now, this is our 3D architecture of AlexNet model. Note that AlexNet doesn't have any 3D visual form. I just made this 3D design so that you can understand it in a better way. So, this is our input image, separated into 3 of its constituent colors: red, green and blue. And the input size of this image is 227 cross 227. Let me add this here. Next is our first layer. Also, this is our convolution layer. All the feature extraction takes place here, as I have shown you previously. Here you can see number of kernels are 96. That means there are 96 layers bind together here. So to calculate the size of convolution, which is our first layer, we have this formula: f minus n plus 1 plus p into 2, which is previous input size minus kernel size plus 1 plus padding into 2. So here we have so it is our first convolution layer. The kernel size is 11 cross 11. So we write 11 cross 11 here. Next, as you can see, the number of kernels are 96. For stride, we have stride of 4. So our input size will be previous input size, which is, you can see, 227 minus kernel size upon stride plus 1. So it will become 55 cross 55. So the size of this convolution layer is 55 cross 55. So we will update it here. 55 cross 55. Our next layer is pooling layer, where we decrease the size of our image while maintaining the features, also to prevent overfitting. So here we have kernel size of 3 cross 3. We have stride as 2. So our input size will be previous input minus kernel size upon stride plus 1, which is equals to 27. So we get the size of this pooling layer as 27 cross 27. So we will update it here. Similarly, for our next convolution layer, number 2, we have kernel size of 5 cross 5. Number of kernel, you can see 256. We have stride of 1, and here we applied padding of 2. So our input will be previous size minus kernel size plus 2p. upon stride plus 1. So we get 27 as the size of this convolution layer. Please 27 cross 27. Next we have pooling layer number 2, where we have kernel size of 3 cross 3 and stride of 2. So our input will be previous input size upon stride plus 1. So we get the size of 13 as this pooling layer. 13 cross 13. Next we have convolution layer number 3, where we have convolution layer number 3, where we have kernel size of 3 cross 3, number of kernels 384, stride of 1 and padding also 1. So our input will be previous input size minus kernel size plus 2p upon stride plus 1, which is equals to 13. So we get 13 as the size of this convolution layer. So here we will update the size as 13. Again we have a convolution layer number 4, where kernel size is 3 cross 3, number of kernels are 384, stride of 1 and padding is also 1. So our input will be previous input size minus kernel size into twice of padding upon stride plus 1, and we get 13 as the size of this convolution layer. So here we update the size as 13 cross 13. Then again we have a convolution layer number 5. Where the kernel size is 3 cross 3. Number of kernels has 256, stride of 1 and padding of 1. So the input will be previous size minus kernel size plus twice of padding upon stride plus 1. And we get 13 as the size of this convolution layer. Now we have pooling layer 3. Where kernel size is 3 cross 3, stride of 2. So the input will be previous input size minus kernel size upon stride plus 1. So we get 6 as the size of this pooling layer. Then we flattened our matrix and fed this to the fully connected dense layer. Where the number of neurons are 4096. And last, we have output layer contains 1000 different classes. So here is our simplified version of AlexNet. Okay, so now let's talk about some of the techniques used in this architecture. Number 1 is ReLu, stands for rectified linear unit. As we know, 10H uses exponential function, which makes it more complex function. And the main problem with the 10H function is that as it reaches a certain point, we can't see any difference in the gradient curve. Because of that, the weight cannot get updated. This is called vanishing gradient problem. So to counter the problem, ReLu was developed. It makes all the negative values as 0 and keep the positive values as it is. Don't worry, I will make more detailed video on all rectification function in the future. Next, they have used GPU parallelization. Using a single GPU or CPU limits the maximum size of the network, and 1.2 million records are far too big for a single GPU. So what they did is, they separated the task over 2 GPUs, results in faster training time. Next is local response normalization. It was the first time that LRN was used. It is the technique of the brightness normalization that helped computer neural network learn from the visual inputs. Next is overlapping pooling. Let's understand with an example. In our first case, we have a stride of 2 and kernel size of 2, or we can say stride equals to kernel size. So suppose we have an 1D array and we have to perform max pooling here with kernel size and stride of 2. So here we get 0 out of these two. Then we shift 2 blocks and get 5. Again we shift by 2 blocks and get 6. Similarly, doing this with the different arrays and get the same output, which is the downside of this normal pooling. So what they did in AlexNet is to use overlapping pooling. Okay, suppose we have the same 1D set of arrays, but we use stride of 2 and kernel size of 3 this time. So here is our array. We take max out of these 3 because our kernel size is 3 and we get 5. Then we shift 2 blocks and take max out of these 3. Now you are noticing that there is overlapping formed in that array. That's why it is called overlapping pooling. Now we do this for the next 2 arrays and get the output. Now you can see that by using normal pooling we get the same output with different arrays, but when we use concept of overlapping pooling we get different output. Next is data augmentation. Data augmentation means taking the training images and adding some modification to the image and train the model with different version of the same images. For example, data augmentation includes flipping the image, rotation of the image, decolorization of the image, adding impurities to the image, and many more. It increases the diversity of the data, and when testing images is different, like low light or tilted, the model predicts it correctly. Next is dropout. Deep neural network tends to overfit the training dataset more. With few examples, we can reduce the chances of overfitting by using different model configurations, but it reduces the computational power as we need to train those extra models. So with dropout, we drop some of the nodes randomly during the training, and by that we get different network architecture, and it helps to reduce the chance of overfitting. Now let's head towards coding part. Hello guys, so now let's make our own model. First we build our model, then we compile it, and then lastly we check for the evolution scores. So here we have imported warnings. We imported Sqeuential, dense, activation, dropout, convolution, wrong areas, patch normalization. We imported numpy, then we get our data set. Then we load our data set. Note that this data set contains 17 types of different flowers. Load data set. Then we create Sqeuential. For our first convolution layer, we have filter size of 96 and we have taken input of 224 cross 224 instead of 227 because the dataset we have contains the size of 224, which make none of the difference. With the activation of ReLu, then we apply max pooling of size 3 cross 3 and stride of 2 with valid padding, and we add batch normalization. Batch normalization. Then our second convolution layer, we have 256 pi 11 padding as valid. Activation of value. Then again pooling layer with 3 1 1 and valid. That's normalization. Then our third convolution layer, 384 3311 and valid, and we normalize activation of ReLu, and we normalize the data set. Then fourth convolution layer, convolution filters 384, kernel size of across 3, stride as 1 cross 1, padding as valid, with activation of ReLu, and we add batch normalization here as well. Then our last convolution layer with 256 3 and 1 comma 1, padding as valid. Then activation of ReLu. Then the last pooling layer with 3 comma 3 2 comma 2 and valid. Then we normalize the data set. Then we pass it to the flattening layer. And add our first fully connected layer. With the activation of ReLu. Then we use dropout of 40%. Then we normalize the data set, and our second fully connected layer. With activation of ReLu. With dropout of 40% again. And lastly, the output layer contains 17 classes with activation of softmax. Then we do the compilation and fit the model with batch size of 5 epochs. Sorry, with batch size of 10 and with 5 epochs. We kept the epochs less because we are limited on computational power and our data set is very less. which obviously the accuracy will be low. But it is to explain you guys. Then we print the loss, accuracy, save our model, print the summary. So here you can see the summary of the model. We have taken the input of 224 instead of 227. You can calculate this with the formula I have teased you earlier. Lastly, you can see the accuracy is very low, which is obvious that we have trained on less epochs and less data. You can train it on your own data and increase the epochs as you want. So yeah, thanks for watching. Okay, so let me introduce to this channel. This channel is dedicated to data science community, and later in the channel you will find detailed videos on all important topics about activation functions, optimizers, machine learning topics, NLP. We will do live programming, make some projects, and I'm also planning to upload a vlog about a project I am working on, which is about an experiment that is human were ever able to successfully adopt AI and successfully be able to be dependent 100% on AI. In short, AI as your sixth sense. Thanks for watching until the end. I hope this video is helpful to you. Comment down below if you have any doubt. Have a great day ahead. Jai Hind, Vande Mataram.